Hello everyone, my name is V. Dinesh and my topic is discrete effects on boundary and my roll number is 536 and my topic is discrete effects on boundary conditions of the lattice-Boltzmann method for convection diffusion equations with curved geometries. In the past 3 decades, the lattice-Boltzmann method LBM been successfully advanced from simulating complex fluid flows to heat and mass transfer processes, which are usually governed by convection diffusion equations CDES. In addition to the lattice Boltzmann models for CDES, the boundary treatment implemented at the boundary nodes, the lattice nodes nearest to the physical boundary, is another important problem. As have been revealed in flow simulations, the discrete effect on a boundary condition also must be minimized to derive reliable results for CDEs. Since the local information of the current node is only contained, the single node boundary technique would be more expected to match the local computation of LBM, especially for the case of complex boundaries and narrow spaces in porous media. With the two relaxation time model, Ginsburg analyzed the single node anti-bounce back boundary condition for CDES. Lattice Boltzmann model for convection diffusion equations. Without loss of generality, the convection diffusion equation considered here are in two-dimensional case. The CDE with the source term is correspondingly written as sigma t into phi plus delta into phi into u equal to delta into d into delta into phi plus r, where phi is the scalar variable usually encompassing temperature concentration. D is the diffusion coefficient. U is equal to u comma v is the convective velocity and R is the source term. In the present work, the LBE equation LBE with the MRT collision operator is employed to solve the CDE. Fi into x plus Ci into delta t comma t plus delta t minus Fi of x comma t is equal to minus of sigma j m inverse S in Sm of ij into Fj minus Fj of equation plus delta t into Ri. This is the equation 2, where fi of x comma t is a distribution function at the position x and time to moving with a discrete velocity ci. Excuse me. Fi equation is the equilibrium distribution function. Delta t is the time increment and Ri is the discrete source term. M is the transformation matrix and S is the diagonal collision matrix. To be concrete but without loss of generality, the discrete velocity Ca conforms to the D2Q9 velocity model. Accordingly, Ft equation j equal to 0, 1 up to 8 appearing in equation 2 takes the linear form. Excuse me. F of equation of x comma t equal to omega j into phi into 1 plus cj into u by c square of t, where omega j is the weight coefficient, cs is equal to c into t, 3 volts is the lattice sound speed. Here, c is equal to delta x by delta t is the lattice speed with the delta x, the lattice spacing. Within a framework of MRT model, the matrix M is used to map the distribution function Fi and its equilibrium distribution function Fi in the velocity model onto the moment variables in the moment space. MF equal to M naught M1 up to M8 power T, comma M equation equal to MF of equation. Excuse me, where F equal to F naught F1 up to F8 power T and F equation equal to F naught of equation, comma F1 of equation up to F8 of equation power T with the D2Q9 lattice model. M can be constructed by the discrete velocities via the Gram-Schmidt orthogonalization procedure and the one form of Mx equal to 1, discrete effect on curved boundary conditions. We now theoretically investigate the discrete effect of boundary conditions for CDS with curved boundaries. Note that the Boundary condition with a curved wall can be treated separately for each velocity direction. As illustrated in figure 1a, the curved boundary is intersected. As you can see in the figure, excuse me, and the first one shows schematic of a curved wall boundary along one single lattice direction. The thin solid line is a grid line and the thick curved one represents the boundary surface. White circles are the fluid nodes, black circles are the intersection point of the boundary with the grid line, and the square box is indicates the solid node outside the computational domain. And the second one shows that the schematic of the boundary arrangement with a distance ratio gamma. Excuse me, with a lattice link from XR to XF along the lattice direction EA is equal to CI by C. In the context of LBM, the unknown distribution function Fi xf comma t plus delta t is specified according to the boundary condition of the after a time step delta t of time t. To simplify the analysis for curved boundary conditions, we consider a unidirectional time-independent diffusion problem between two parallel plates, which assumes that u is equal to constant, v is equal to 0, and delta into sigma into x into phi equal to 0. The bottom and top plates are stationarily located at y equals 0 and y equal to h, respectively assigned with constant phi b and phi t. Further, with the source term defined by r equal to 2 into d into delta into phi by h square, where d into delta into phi equal to phi of t minus phi of b. The analytical solution to be considered problem can be derived from the CDE. Excuse me. Phi of I equal to phi of b plus delta into phi into y into h into 2 minus phi by h. This represents the equation is the MRT model of 2 with D2Q9 lattice is the employed to solve the above diffusion problem. After a collision step is executed for every node at a time t in the t's. Excuse me. F dash of I x comma t equal to fi of x comma t minus sigma j into m inverse sm of ij into fj minus f of f equation j plus delta t into ri. This represents equation 9. The streaming step is fi into x plus ci into delta t comma t plus delta t equal to fi dash of x comma t. This represents the equation 10. Can be implemented for all inner lattice nodes at time t plus delta t. However, for the boundary nodes nearest to the wall, say the bottom plate as shown in the figure 1b, F0, F1, F3, F4, F7, and F8 at the layer j equals 0 can be determined after the streaming step. The inner distribution functions F2, F5, and F6 are unknown and must be specified by the boundary condition. Excuse me. The discrete effects of boundary conditions were analyzed within the framework of MRT model for CDS with curved boundaries. For previous curved boundary conditions which only contain the distance ratio gamma, the mathematical derivations that the relaxation time tau t to eliminate the numerical slip should be changeable with the distance ratio. By virtue of free parameter L besides gamma, a theoretical strategy based on a curved single node boundary scheme is provided to achieve the uniform tau 2 tau 2 while the numerical slip can be removed successfully. Two different problems with inclined or curved boundary geometries are simulated to validate our theoretical analysis. It is unequivocally revealed that the discrete effects that curved boundary walls cannot be eliminated for halfway boundary scheme with the relation tau 2 equal to 4 tau 1 minus 1 by 2 1 by 2 by 4 into 2 tau 1 minus 1. In addition, the numerical predictions with our derived relation have superior accuracy than those with other choices of L. The availability of our theoretical results is further examined for a natural convection between two cylinders. To support the accuracy of the proposed treatment for complex curve geometries, it is noted that the variable phi in the near wall region should have a parabolic distribution. This assumption has been adopted in some previous studies to acquire reasonable results, but compared with extending the BGK model to other advanced LBA models, example, the TRT and MRT model. For CDEs, we would like to note here that resorting to more degrees of freedom from the boundary condition may have more potential to eliminate the discrete effect at curved boundary geometries with uniform relaxation times. That's it, and thank you everyone.